Hi class. In this section, we are covering the case of non-homogeneous equations. So what makes our equation non-homogeneous is the right-hand side. The left-hand side is going to be the same as we've been studying. We have a second order linear equation with constant coefficients. But on the right-hand side, before we had 0 on the right-hand side, and that was our homogeneous case. Now we have some function just with t's in it, no y's. And this is the non-homogeneity, which is sometimes called the forcing function. And you can think of that in the mass spring analogy as if you had some external force on the spring, like something was shaking it. So that's forcing function is pretty common terminology in physics. So we're going to call this general form NH for non-homogeneous. So obviously this adding this f of t to this equation makes the problem significantly harder to solve. And so we are going to spend a few sections on this. And this section we're just going to do basically some guessing. We're going to guess at the solution based on what the non-homogeneity would look like. And we will sort of develop this theory and these methods over the next couple sections. So let's just start with an example that we'll work through to get an understanding for the method. So here's our equation. Y double prime plus 3y prime plus 2y equals 3t. So let's think about what sort of function might be a solution to this. We know that y is the thing that we're trying to solve for. And so we need to take second and first derivatives and then combine all three of those functions together in a linear combination, and then they need to add up to 3t. So obviously the function's not going to have like an exponential in it or a sign or anything crazy. It's probably just going to be another, it should be something that kind of looks like 3t because when you take all those derivatives, um, they still kind of look like 3t. So let's take a guess. Guess one. Let's say it's something that looks just like 3t. So maybe some other t. So some a times t. A is a constant. And then y prime equals a and y double prime equals 0. So then when you add them all up, you get 3a plus 2at equals 3t. And what we get from there is we need the a terms to kind of match up with 0, and then these match up with the 3t. So you need 2a to equal 3 and 3a to equal 0. But of course that's not going to work. So that's a problem. Now let's try another guess. And you can tell by my color choice that this is going to be the correct one. So what we were missing here was a constant term. So maybe our guess wasn't, maybe we needed some constant term here because, you know, if we had a square, if we had like a t squared, then that would get screwed up because you'd get t squareds that wouldn't match up over on the right hand side. But if we had a constant term, maybe those will kind of get canceled out and you'd get some consistent set of equations down there. So let's take our guess. Y equals AT plus B. Okay. Let's see, let's make it a little smaller. And so then we have Y prime equals A and Y double prime equals 0, same thing. And then we end up with 3A plus 2AT plus B equals 3T. And we can combine, we're going to combine all of the t terms together and all of the non-t terms together. So that gives us 2at plus 3a plus 2b equals 3t. So now we're going to match up these terms. So we have 2a will match up with 3, and then we can think about this as being plus 0. So that constant term will have to match up with 0 over there. So then the set of equations that we get is 2a equals 3 and 3a plus 2b equals 0. And I'll let you work out the arithmetic there. I'll just give you the answer. A equals 3 over 2 and b equals negative 9 over 4. So then our final answer is y equals 3 halves t minus 9 fourths. And let me just point out that this is a particular solution to the differential equation. Okay, you notice it doesn't have any constants in it. And we didn't even have any initial conditions. So if we had initial conditions, we wouldn't be able to make sure that this satisfied them because we don't have any constants to kind of manipulate here. So this is not, so the opposite of it, or the contrast to a particular solution is a general solution. I've used these terms a lot before, and I'm not sure how well that I've really defined them, but that's kind of the difference here. The particular solution is just one function that can fit into the differential equation. The general solution is the entire family of functions. So this would have constants C in it. So in this particular section, because we're just sort of introducing this concept, we're only finding particular solutions. We're finding a way to find something that fits into the equation. And then in future sections, we're going to generalize that out, right? Okay. So now the method that we have just done is called the method of undetermined coefficients for maybe obvious reasons, because you have some coefficients, A and B, and they are undetermined when you start out. So you start off with some form of a function with some coefficients in it, and then you plug them in and you determine the coefficients. So that's what this method's called. And so this method is actually really, really simple. I mean, all we did is a little bit of really basic algebra. And so the problem here is that this will only work with certain forcing functions. But there are a few that it works with, and they're pretty common ones, especially since, you know, the book chooses to give you ones that the method that you learn will work with. So here's a little table about which forcing functions, which right-hand sides you make what kind of guess with. Here we go. We've already seen an example of this first one. So this is a monomial, a power of t, and you might have some constant out in the front, c. And so just like we saw, we want to have our guess is going to be a polynomial of the same order, but with all the smaller terms as well, all the lower order terms. Okay, so if you've got your term on the right-hand side that's a t to the m, then your guess is going to be a polynomial that starts with t to the m, and it might have all these lower order terms. So if m was 2 and you had some t squared, your guess would be like, you know, a t squared plus bt plus c. They just have to use all the a, naught, and everything because there's some arbitrary number of them. So this is trying to be as general as possible. All right, so our next one is if we have an exponential term. And again, an exponential term makes a lot of sense if you look at the original equation, because when you take derivatives, they still look like exponentials, and so you're still going to just multiply together. So, or you're just going to like add a bunch of copies of that e to the rt together. So if you have something e to the rt, r, c is a constant and r is also a constant, then your guess is going to be another exponential with the same r, because you don't have any way of changing that when you're taking the derivatives, but maybe a different constant here. So sines or cosines, so this guess works with both sine or with cosine of beta t. Again, beta is a constant. You know, when you take derivatives of sine or cosine, they flip back and forth between sine and cosine. And so you might be adding together sines or cosines. So your guess has to have both a sine term and a cosine term. Same guess whether your right-hand side is a sine or a cosine. And then the last one is a combination of a power of t and an exponential. And your guess is just going to be the same thing, a combination of the whole polynomial up to your power m times an e to the rt. And we'll see some examples of some of these of how they work out. So let's take our first example. That's going to be y double prime plus 3y prime plus 2y equals sine t. So this is, again, pretty straightforward. Our guess is going to be y of t equals, remember, go up to our table. We need a sine term and a cosine term. Our beta in this case is 1. So let's do a sine t plus b cosine t. And we can take our derivatives. So we get a cosine t minus b sine t, and y double prime is negative a sine t minus b cosine t. Plug in, and we get this. This is just plugging in my y prime and y double prime. And now I can group terms, switch colors. So group sines and cosines. And then we can compare things. So that's going to give me this. Now I can put all of the coefficients on the sines and everything together. So that's going to give me negative a minus 3b plus 2a sine t plus negative b plus 3a plus 2b cosine t equals sine t. Now, the deal here is that cosine and sine are linearly independent functions, okay, which means that they can't add up to each other, okay? So we really have over here plus 0 cosine t. And so with linearly independent functions, if you have some linear combination of them, which we have here, we have a constant times sine plus a constant times cosine. They're never gonna like cancel each other out. So the sine terms have to equal the sine terms and the cosine terms have to equal the cosine terms. So that tells you that the coefficient on sine is going to have to equal 1, and the coefficient on cosine is going to have to equal 0. So you've got now two equations to solve. these two, where I simplified the terms in the parentheses up here a little bit. And then I'm going to not do this arithmetic in person or, live, and I'll let you verify that we end up with A equals 1/10 and B equals -3/10. So then the particular solution that we were looking for is just the guess that I had with my actual coefficients filled in. Okay, so that's the whole gist. Now let's do another example. So here we are. Y double prime minus 6y prime plus 9y equals e to the 3t. So our guess is going to be, because our right-hand side is an exponential, e to the 3t, our guess is going to be y equals a e to the 3t. And then we have our y prime equals 3a e to the 3t, and y double prime equals 9a e to the 3t. So we plug in, and we get this. So we get, 9a minus 16, or minus 18a plus 9a all times e to the 3t, because all of these terms have an e to the 3t in them, and that equals e to the 3t. But here's a problem. That cancels. So this gives us that 0 equals 1, which is a contradiction, obviously. So what went wrong? So the problem is that when we plugged our guess into the left-hand side, everything equaled 0. So we actually have that our guess is a solution to the left-hand side. Nine y plus 9y equals 0, i.e. the homogeneous equation. So you can see that if your guess, because remember when we did the homogeneous equation, let's sort of see what happened there. If we had our homogeneous equation, we would find the characteristic polynomial. So that's r squared minus 6 r plus 9 equals 0, and we can factor this into r minus 3 squared. And so we have that r equals 3 is a double root. So then we get that e to the rt, or e to the 3t, and t, remember when we had a double root, our second linear independent equation was e to the 3t, t to the 3t, are both solutions to the homogeneous equation. So if they're solutions to the homogeneous equation, then you put them in the left-hand side and it equals 0. So then they can't be solutions to the non-homogeneous equation if the right-hand side is not 0. And neither can a constant multiple of it. Okay, so I guess I would just add that c e to the 3t and c t e to the 3t are solutions, because remember we were able to find the general solution to that homogeneous equation. Even if you multiply your solution by a constant, it's still going to equal 0 on the right hand side. So these general kind of solutions also can't be solutions to the non-homogeneous equation. Okay, so we need to take this into account when we're making our guess. So let's see, we need a new guess then for this equation. Our e to the 3t didn't work. when we were doing our double root case before, and we had, we found our one solution was e to the 3t, and then we needed another solution. The thing we guessed was multiplying it by a t, because that t times an exponential sort of still um, worked out in the linear combination. We probably can't guess t again. We know that t e to the 3t is not going to be a solution here. So we will, a natural sort of guess would be to guess a t squared. So that's going to be the guess that we make. Y of t equals a t squared e to the 3t. And I'll put a note over here. I would say that, you can check that y equals a with just one factor of t, a t e to the 3t doesn't work. Okay, so let's go back to our t squared guess and see if this does work. So y prime, we got to do product rule here. So we get a 2a t e to the 3t plus 3a t squared e to the 3t. Y double prime is, again, product rule, so this is going to get a little bit gross. 2a e to the 3t plus 6a t e to the 3t plus 6a t e to the 3t plus 9a t squared e to the 3t. Hopefully I'm doing all this right. Okay, so we need to plug this in, so I needed to remind myself what the equation looks like. So I drag that down here, and let's plug in. And I'll just do some shortcut, and you can verify all the arithmetic. So what I've done here is grouped. So I plugged these guys into my equation. So I had to multiply them by the -6 and the 9. And I've grouped them by the terms that had t squared e to the 3t, and then the groups, and then the ones with t e to the 3t, and then the ones with just e to the 3t, because those are my three linearly independent solutions here. These functions are linearly independent, and so those are going to be how I compare my coefficients. So fortunately, that cancels and that cancels, which is good because those t don't have anything on the right-hand side, and so those have got to equal 0. If they didn't equal 0, then we have a problem and we've got to do something else. And so what we end up with is 2a equals 1, so a equals 1/2, easy enough. And so our particular solution is 1/2 t squared e to the 3t. Okay, and so I'm just going to remind you all again that this is just one particular solution to our equation, but isn't the whole story, as we will see in future sections. Okay, so to summarize, I'm going to put up another table. The table I had before was not really very precise, right? Wherever that table was, yeah, over here. That was just sort of like, what you might guess, but we had some potential problems. So the real table is actually written in the book, and I'll paste it here. All right, so here it is. This is on page 178 in the book. My table looks a little bit different because the PDF I have is of an old edition of the book, but all the text is the same. Okay, so this summarizes everything that we've done in this section. To find a particular solution to your non-homogeneous equation when your right-hand side is a power of t times an exponential, your guess is going to be the same thing we had in the first table, our polynomial of power m and our exponential. But we will need to add this t to the s, it's either going to be t to the 0, which is just 1, so you don't have to add anything, if r is not a root of the auxiliary equation. So that means that another way to say that is that, i.e., if e to the rt is not a solution to the homogeneous equation. And then if it is, then if it's a simple root, if r is a simple root of the auxiliary equation or characteristic equation, then you need to add 1 power of t. And if it's a double root, like we saw in that last example, then you have to add 2 powers of t. And then we didn't see an example of this, but the same thing is going to end up being true with our cosines or sines. So in this case, you'll see that this table has grouped things more clustery than the table I wrote before. It's sort of grouping everything together. So if you've got a power of t and an exponential and a cosine, you're going to run into trouble because remember that e to the alpha t times cosine beta t is what your solutions look like in the case of complex roots. So if you're if you don't have a if you're not a root of the auxiliary equation, then you don't even have to worry about the t to the s. So that's going to be, s is going to be 0. You can just ignore that. And you can just put your polynomial and your exponential and your cosine plus the same thing with a polynomial, an exponential, and a sine. Where you will run into trouble is if your alpha plus I beta is a root of the auxiliary equation, in which case, if this happened, that means that e to the alpha t times cosine of beta t and e to the alpha t times sine beta t are solutions to the homogeneous equation. So in that case, then you're going to have to add this power of t to both terms. Okay, so I don't know. I know that this is like sort of a lot. This is like this table here is everything that we just did plus the previous sections all like sort of clustered into one box. So really do work out the examples in the homework and things should become a little bit clearer once you do it yourself. Okay, so that's the method of undetermined coefficients. I will say in a preview of our next section, I will point out that we've only talked about one term on the right-hand side. So we haven't talked about something like t squared plus t plus 5 or whatever. This is just a single term. And there's a really simple way of dealing with multiple terms that we'll talk about next time. And so that's it for this section. Thanks.